Willkommen! So, we had just finished talking about sp3 hybrid orbitals, which are a collection of orbitals that are all exactly the same, and they point in different directions in a sort of tetrahedral arrangement. So, how do we carry on from here? How do we form a fifth bond, a sixth bond, in order to get those larger structures? Well, remember why we're able to form that expanded octet in the first place, why we're able to get a fifth bond and a sixth bond. It's because we're looking at the third row of the periodic table and below, and they have d orbitals available. So this is dsp3, or sp3d. I've seen it both ways. And similarly, to get, that's for 5 bonds, and similarly for 6 bonds, it could be d2 sp3 or sp3 d2. Okay. I prefer these two, but I wouldn't yell at you if you did it the other way. I might yell at you. I might. But that's the hybrids we get for the larger molecules. So in order to know how many and what kind of hybrid orbitals you need, just count the electron domains. You need 1 hybrid orbital per electron domain. So hybrid orbitals don't just cover bonds, they also cover non-bonding pairs. So we can look at, for example, water. Here's HOH, boom, boom. Okay. This meshes perfectly with Lewis. You just draw out the Lewis structure, then count the electron domains. Boom. So oxygen has 4 electron domains, so it needs 4 orbitals. So it's going to be sp3. 1 plus 3 equals 4. Okay. And then you look at, say, pf5. Well, that is So that is pf5. Okay, it has just those 5 fluorines. It has 5 electron domains, so it needs 5 orbitals. So it is sp3d. 1 plus 3 plus 1 is 5. So it's really easy to come up with the hybridization for your hybrid orbitals. Drawing the actual orbitals would be a lot more difficult. So, for the most part, I'm not going to ask you to do that. When I say for the most part, I mean I would limit myself to these, because you can draw these in 2 dimensions. They are really, really easy. Trying to draw 4 dimensions, trying to draw 4 orbitals in 3 dimensions can get really, really messy. Okay, so I won't be asking you to do that. Okay, now multiple bonds require more work. They require additional explanation. So, we're going to look at carbon dioxide and formaldehyde to look at how a hybrid orbital theory and so on, and valence bond theory, because this is sort of where valence bond theory kind of comes into it, to explain what multiple bonds are and how they work. So, carbon dioxide, CO2, is just a nice, straightforward, straight line. Carbon has 2 electron domains, so it needs 2 hybrid orbitals. So it's going to be sp hybridized. So sp, and that covers the 2 initial bonds that carbon forms with oxygen. It's very straightforward, and it is nice and happy. But now those 2 hybrid orbitals only cover 2 of the bonds. We still have 2 bonds unaccounted for. We need to know how and why those bonds form. Where do they come from? Fortunately, carbon has 2 orbitals left over. It has its 2p orbitals. Okay? It started out with s and 3p. It used up those 2. It has these 2 left over. So those are the orbitals that it's going to use to form its additional bonds. But they're not going to be hybrids. These 2 are different. Each one is going to be, first off, it's going to be purely p in character. It's not going to be hybridized with s. But it's also not going to be a hybrid. It's just going to be the individual p orbital. And what it looks like is, okay, so here's the carbon atom, and here's an oxygen atom. Okay? And here's carbon's p orbital, and here's the corresponding p orbital in oxygen. It has to be pointing up and down like that, because it already used the orbitals pointing toward the oxygen to make the sp hybrids. So it doesn't have that p orbital available. So what happens is, this is sort of like valence bond theory. Okay, these two bonds sort of overlap and mix and intermingle above and below the sp hybrid. Okay. So this first bond, this sp hybrid, is directly between the two atoms. But this bond here, the second bond, is above and below. And because they are different kinds of bonds, they have different names. This one down here is called a sigma bond. This is a Greek letter sigma. The capital sigma looks, that's awful, looks like this. That's the capital sigma. And this is the lowercase sigma. It's just an O with a tail coming off to the side. So we use the lowercase sigma to talk about hybrid orbitals, because they have S character. And sigma is the Greek letter S. Okay. Up here, this bond, all it has is P character. It has no S, so we call it a pi bond. And that shows up again all the time. Pi bond versus sigma bond, that sort of nomenclature is incredibly common. So you had better get used to it. Let's look at formaldehyde now. The molecular formula is CH2O. So when you look at it, you have carbon double bonded to oxygen, and then bound to hydrogen. Oxygen has non-bonding pairs. So this carbon has 3 electron domains, so it needs 3 hybrid orbitals. So that means they are going to be sp2 hybridized. And sp2 hybridized means that we have 1 p orbital left over. This means we have this, and this, and this sitting on top of the carbon. And these are our sp2 hybrids. And then you flip it on its side, and you got, here's the carbon, and you have bonds, sort of lying on top of it. And then you have this guy, pure P, above and below, forming a bond with oxygen over here. Now the interesting thing is that the oxygen is also sp2 hybridized, because it needed to form 1 hybrid orbital to take into account the bond, but another one for each of the non-bonding pairs. So both carbon and oxygen are sp2 hybridized, but you can only really see it with carbon because it has 3 atoms bound to it, whereas oxygen has an atom and 2 non-bonding pairs. Here's another interesting little tidbit we can discuss. We already talked about carbon. One of its bonds looks like this with oxygen. And then, coming over to the other side, here's its other sp hybrid, forming a bond with oxygen. Each of the oxygens, by the way, is sp2 hybridized, because it has 2 non-bonding pairs. Now, this is the weird thing about the double bonds. One double bond, okay, so let's go ahead and say this uses X. One of its bonds is going to use py, the other one is going to use pz. They're pointing along the 3 different axes, the x-axis, the y-axis, and the z-axis. So one of its double bonds will, be above and below, using the remaining p orbital available to the other oxygen. Let's call this py for oxygen, py for carbon. But the other oxygen can't do that, because this carbon has already used its py, so this oxygen has to use pz. So does carbon. So this double bond is in front of and behind the molecule. So this is above and below. This is in front and behind. So this can have real implications as well for the way molecules can behave. But the last example I'm going to show you for this is going to be ethane. Or sorry, not ethane, ethene. Ethene is swamp gas, C2H4, and it looks like this. And if you're wondering what I meant on the pronunciation, it has an E instead of an A, and that refers to the double bond right there. Now this has this particular implication. These bonds, these single bonds, are free to rotate. Because they're a hybrid, they're located only between the two atoms. So you have ethane over here. This bond for ethane is perfectly free to rotate. So these hydrogens, can be spinning any which way. Okay, but this double bond is locked down. Okay, it can't rotate because it has that the non-hybrid pi bond. And that pi bond is only, above and below the bond. It can't rotate. So, sigma bonds rotate. Pi bonds are locked. That means that ethane can rotate. Ethane can rotate. Ethene is perfectly flat and does not rotate. And that's another sort of characteristic of sigma and pi bonds that plays a big role in chemical behavior, especially if you keep on going and study organic chemistry. Because organic chemistry, sometimes you have single bonds, sometimes you don't, and that can really change the way organic molecules can behave. Now, the last bit is molecular orbital theory. And this sort of combines everything in Vesper and valence bond theory and hybrid orbital theory to come up with these complicated but incredibly powerfully descriptive diagrams. So remember how I was talking about px and py and pz and all that stuff, and the positive and the negative, and how this comes up with different orbitals? Well, you can have bonding orbitals and anti-bonding orbitals, so sigma and sigma star. You can have pi and pi star, and you get all this stuff, and it is really, really powerful for explaining, the strengths of various bonds, and why some bonds form and others don't, and the electronic behavior of different molecules, why some things are magnetic and some things aren't. It's really powerful, but it's also really complicated, so we are not going to cover it in this course. I mean, I love it to pieces, but it makes baby Jesus cry. So we're not going to go there. But that is it for this set of slides. Once again, practice, practice, practice. Practice drawing your Lewis structures, and from your Lewis structures, get your electron domains, your electron domain geometry, and your molecular geometry. And then from molecular geometry, you can get your hybrid orbitals. And that is definitely what I expect you to know. Oh, and polarity. You need to be able to get polarity out of molecular geometry. Okay, I will see you later.